So ultimately, we're going to talk about how to find confidence intervals for three things. We're talking about confidence intervals for a proportion, confidence intervals for a mean, and confidence intervals for a variance. Right? And we're going to start off, or we're going to start our discussion here, talking about confidence intervals for a proportion. I've got one more term for us to add here to our glossary. The margin of error. This is the key thing that we're going to be calculating to find a confidence interval, right? The margin of error is the maximum likely difference with a given probability, right? That's the confidence level, between the observed sample proportion and the true value of the population proportion. So what we're going to do is we're going to know p hat. That's our sample proportion. We're going to calculate that from our data. And to get our margin of error, what I'm going to do to get our confidence interval, I'm going to add the margin of error, and that's going to give us the upper limit. And I'm going to subtract the margin of error, and that's going to give me the lower limit. And what I'm claiming is I am 90, 95, 99% confident that the population parameter is in that range. Okay, so here's how we do it. There's a lot going on, but the key thing, focus on the formula down there in the bottom left-hand corner. That is the formula that we will use to calculate the margin of error, right? And once we've found it, you see what we've got over here is exactly what I just said. You add the margin of error to the sample proportion, and you subtract it from the sample proportion. There's our confidence interval. So what are all the terms here? E is the margin of error. N is the sample size. P hat is the point estimate. The best point estimate for the population proportion is the sample proportion. Q hat is 1 minus P hat. That's the not probability, if you will. And finally, we have Z alpha over 2. That's the critical value we talked about on the last lecture based on our given confidence level. Okay, so, and I warned you earlier, right, we're talking about the central limit theorem. We're always going to have conditions with these things, conditions that we have to think about and make sure are met before we jump in and start using these formulas. So to use this margin of error formula, I have to check three things. First, the sample must be a simple random sample, right? The sample has to have been selected properly, if you will. The conditions for a binomial distribution have to be satisfied, and there have to be at least 5 successes and at least 5 failures in the sample. All right, so let's take a look at an example. Look at this one. In a Harris poll, 514 human resource professionals, 90% said that the appearance of a job applicant is the most important thing. Notice what we've got here, 90%. That's a percentage, 0.9 would be the corresponding proportion. So I've been given a sample proportion here. All right, this is going to be our P hat. So what I want to do is I want to construct a 99% confidence interval for the proportion of all human resource professionals. And that's kind of a key point I want to emphasize here. We are always creating confidence intervals for the population, for all professionals in this career. All right, the proportion of professionals who believe that appearance is most important. All right, so first, confirm requirements. Harris is a very reputable polling agency. It's safe to assume they know what they're doing. They follow the proper rules for collecting a random sample. This does meet the requirements of a binomial distribution. There are only 2 possible outcomes. Either they said yes or they said no. And it is reasonable to believe that one human resource professional's response is going to be independent from everybody else's. So how about 3? Well, look, 90% of 514 said yes. Okay, so 90% of 514, that's 463. That's greater than 5. We had more than 5 yeses, right? And if 463 said yes, subtract that 5 from 514. 514 minus 463, That gives us 51 who said no. That's also more than 5. All the conditions have been met. Okay, so we're going to go to the formula. Right? The formula says the margin of error is z alpha over 2 square root of p hat q hat over n. All right, so let's get our values now. P hat, that's the sample proportion. That's 0.9. Q hat is 1 minus p hat. In other words, those are the ones who said no, it isn't the most important thing. That's 0.10. Our confidence level is 90%. That's 0.90. That means alpha is 1 minus that. Or, whoops, I'm sorry. No, I'm sorry, the confidence interval is 0.99. I was looking at that proportion there. Is 0.99, which means this is 0.01, which means alpha over 2 is 0.005. Okay, so to find z alpha over 2, go to your standard normal distribution table, or go back and look at the numbers that you wrote down. Right, it's also down at the bottom of the table that you're looking at. It's probably down there as well. And you'll see z alpha over 2. Remember, there's really two of these, right? There's the left-hand one, which is negative, and the right-hand one, which is positive. We're always going to take the positive one. So this is 2.575. Now it's just plugging numbers into the formula. Right? This is 2.575 square root of 0.9 times 0.1 over, I left n off of my list, didn't I? And that's the sample size. That is 514 people. Right? Now you go to your calculator. This is 0.0341. That's my margin of error. About 3.4%. Right? It's about 3.4%. So, what is our confidence interval? You can write this two ways. I could say it's 0.90 plus or minus 0.0341. Or you could write this as percentages. I could say it's 90% plus or minus 3.41%. Right? Either one would be fine. Okay, so I want you to try doing this one. It's practically identical to the last one. All I did was I changed the confidence level. Right? I dropped it from 99% down to 80%. So I want you to kind of think through the calculations again, right, and see what impact that had on the margin of error. Okay, so a lot of what we did on the last slide is going to be the same. P hat is still 0.9. Q hat is still 0.1. N, the sample size, is still 514. Really, the only thing that's going to change is z alpha over 2. Right, and this, if you go to right, so let's work this through a little bit. If the confidence level is 0.8, then alpha is 1 minus that, or 0.2. Alpha over 2 is half that, or 0.1. That's the number you're looking up in the standard normal distribution table. And if you do that, you should get 1.28 for your critical value. So now we go to the formula. E is z alpha over 2 square root of p hat q hat over n. This is 1.28 square root of 0.9 times 0.1 over 514. And this comes out to 0.0169, right? Which means my confidence interval is 90% plus or minus 1.69%. Now, you notice it got a lot smaller, right? It got a lot smaller. A half more in the neighborhood, right? And that's what we expect. if you're willing to accept less certainty that you're right, yeah, you can get a much more narrower range. Okay, so what's next? Now we've seen how to create confidence levels, right, or confidence intervals. The next question we want to ask is, and this is a very important question from the statistical research perspective, what sample size do I need to get a certain level of confidence in my result? Right, that's the question we're going to answer in the next lecture. All right, so I've got one more thing to think about here, right before we move on. Given a 98% confidence interval, find the point estimate and margin of error. Okay, so now I'm kind of asking to go backwards, right? How can we go backwards? Well, remember what's happening here, okay? We start with p hat, then I add e, and I get this upper value, 3.21, and I subtract e, and I get this lower value, negative 2.51. All right, that p hat value, it is centered in between the upper and lower bound, right? So I can find this p hat just by averaging these two values. P hat is equal to the average of the upper bound and the lower bound. That is 0.35. 0.35. And now I can find the margin of error just by finding this distance. The margin of error is 3.21 minus 0.35, which is 2.86.